All right, let's talk about something that's absolutely critical for safety and reliability in any electrical system: the internal separation in low voltage switchboards. This is a core concept for anyone designing or working with these systems, so let's just dive right in and demystify it. So, here's how we're going to break this down. First, we'll cover why this is so important. Then, we'll get on the same page with the terminology, the building blocks, if you will. After that, we'll walk through the different forms, from the real basic stuff up to the most advanced, and then wrap it all up by talking about how you actually choose the right one for the job. Okay, so first things first, why does this all matter so much? To really get why the different forms even exist, you have to understand the dangers that are literally lurking just behind that panel door. What are we really trying to protect against here? Just think about it for a second. You've got an engineer, maybe it's you, opening up a live switchboard to do some maintenance or run some diagnostics. What are the immediate life-threatening dangers they're facing? Because, let's be honest, the consequences of a mistake in there can be incredibly severe. Yeah, that quote really lays it out in the starkest terms possible, doesn't it? The number one, absolute top reason for internal separation is protecting human life. That's it. At their core, these are all just physical barriers, meant to stop an accidental and potentially fatal touch. But it's not just about personal safety, as critical as that is. Separation does a few other really important jobs. For one, it contains faults. A nasty short circuit in one compartment won't take down the entire board. This also makes a whole system way more maintainable, because you can safely work on one circuit while the others stay up and running. And, of course, you've got to meet the standards like IEC 61439. Okay, so before we can start classifying the different forms, we need to make sure we're all speaking the same language. Separation is all about putting up barriers between three key things inside that switchboard. So let's define what they are right now. First up, we've got the bus bars. The easiest way to think of these is as the main power highways inside the switchboard. They're these big, heavy-duty conductors that carry all the current and distribute it out to the different circuits. Next up are the functional units. So, if the bus bars are the highways, these are kind of like the exits and interchanges. We're talking about your circuit breakers, your motor starters, the actual devices that are doing the work of controlling and protecting all those individual circuits. And finally, you have the terminals. Sticking with our highway analogy, these are the on-ramps and the off-ramps. They are the specific points where the external cables, coming from motors or other loads, physically connect to those functional units. All right, now we know what we're separating: the bus bars, the functional units, and the terminals. So let's see how we actually do it, starting with the most basic levels of protection. Form 1 is, well, it's about as basic as you can get. There are zero internal barriers. None. When you open that door, everything is just sitting there together in one big compartment. It offers the least amount of protection, for sure, and you'd only use it in the simplest, lowest-risk situations. And you can see it right here. It's pretty much a free-for-all inside. The bus bars, the breakers, the terminals, they're all just sitting out in the open. You can imagine how a dropped wrench or just an accidental touch could cause a really, really bad day. Now with Form 2, we get our first critical layer of safety. This is where a physical barrier gets put in place to separate those main bus bars from all the functional units. You can see that key addition right there. That partition now shields those main bus bars, and that immediately makes things safer. The risk of accidentally touching those main power highways while you're working on a single breaker is way, way lower. Okay, now we're moving up to the big leagues. We're getting into the higher forms of separation, the kind that are absolutely essential for things like industrial plants, critical power systems, and any high-risk environment where safety and uptime are just non-negotiable. Form 3, this is a huge step up in both safety and reliability. It takes everything we had in Form 2, so the bus bar is already separated, and then it adds individual compartments for each and every functional unit. And this is where you really see the payoff. Each circuit breaker is now tucked away in its own little cell. So if a fault happens on one feeder, the arc flash, the damage, it's all contained. It keeps it from spreading to the breaker next door and causing a much bigger outage. And that brings us to the top of the mountain, Form 4. This is the most comprehensive protection you can get. It takes everything from Form 3 and adds one last critical barrier. It separates the terminals for each functional unit, too. Take a close look here. On top of all the other barriers, we now have these shrouds around the actual cable connection points. This gives an electrician maximum protection when they're terminating or testing cables on one circuit because they are completely isolated from the live terminals of the circuit right next to it. So we've got forms 1, 2, 3, and 4. The big question for any engineer is, okay, that's great, but which one do I actually need? And the answer really comes down to balancing risk, what the operation needs, and of course, cost. This table really lays it all out for us, doesn't it? It perfectly summarizes the journey. As you go from Form 1 up to Form 4, you're just adding more and more layers of separation, which increases both safety and how easy it is to maintain. You'll see Form 2 a lot in commercial buildings, but Form 3 is often the starting point for critical industrial plants. And for the highest risk places like oil and gas, yeah, Form 4 is the standard. And this insight from an R&D director really drives that point home. In heavy industry, the decision isn't just about meeting the minimum safety code, it's pure economics. That extra cost for a Form 3 or Form 4 board is nothing compared to the millions of dollars a plant could lose from just 1 hour of downtime. Operational continuity is a massive driver. And that really is the crucial question every single design engineer has to answer. For your next project, where do you draw that line? It's always a balancing act between the project's budget, what the law requires, and the ultimate goal, which is to protect people with a robust, reliable system.